So first I like to thank the organizer for giving me this opportunity to present our work. So they are my collaborators, so I'll present on behalf of all of them. So in 21 centimeter observations, what we observe is basically the intergalactic medium, the neutral hydrogen is there, and there is a background sources CMB, and it's passing through the IgM, and we measure the relative brightness temperature as compared with the CMB. That is the 21 centimeter fluctuations we want to measure, and it depends on that spin temperature and the radiation, basically the CMB. And based on the relative amplitude of these two, either it will be absorption or emissions. So how it looks like as a function of redshift from the initial stage. This is basically the absorption and at the later stage, basically the post reionization, the signal will be 0, and when the reionization begins, it will be emission. So depending on which redshift we are trying to measure, the amplitude will be either absorption or the emissions. And this is the neutral, completely neutral, and when the first source of as Suman mentioned, the first source appear, it will start ionizing the intergalactic medium, and we see this. But it is not the whole story, because we are not, when we start the observations, it is not like the 21 centimeter. Lot of other complications arise because of the foreground, our own galaxies, the synchrotron emissions and the system noise, which is much higher as compared to the. So somehow we have to remove them to get rid of the go to that level of the sensitivity to measure the 21 centimeters. So that is the generally two approach people use to remove the foreground. What is the foreground removal? We assume that the foreground is much smoother as a function of frequency compared to the 21 centimeter signal. So what we do generally, we remove the smooth component from the observations, and what is the residual, that is we believe that we can remove. If there is spectral structure also, it will affect the signal, that will some leakage. Another thing is that foreground avoidance. Whatever the smooth frequency dependence, if we plot them as a function of k perpendicular and k parallel, that is the Fourier space, the smooth component will reside in this wedge-shaped region. So no need to remove, just avoid this part of the Fourier space. And we will concentrate, this is the UR window, we can concentrate only this part of that Fourier space. There will be some signal loss, there will be some sensitivity will be gone, but we can focus on this part of the K space to get rid of the foreground part. So that is the two methods generally people in the community use to get rid of the foreground part. But again, the noise will be much higher as compared to the signal. So instead of all the current observations are not that much sensitive to measure the 21 centimeters. So generally we use this power spectrum technique, that is the statistical quantity, to increase the sensitivity. So this is the 21 centimeter, we do the Fourier transform, and then we are measuring the fluctuations as a function of Fourier mode, and this is the power spectrum we are interested. So our aim is to measure the Fourier component, or basically the power spectrum, the amplitude of the Fourier component as a function of k, to measure the 21 centimeter power spectrum. So this is one of the sensitive telescope GMRT, and this is the 21 centimeter fluctuations. The radio interferometers, it measures the Fourier component, basically the Fourier transform of the brightness temperature fluctuations. And if we use this Fourier component measured at different Fourier modes, what we want is the 21 centimeter power spectrum. So that is the aim of this 21 centimeter observations. We have the fluctuations as a function of redshift at different part of the universe, and what we will measure as a radio interferometers, we have the Fourier component at the mode, and we have to remove the foregrounds, and finally we will measure the 21 centimeter power spectrum. So that is the whole story in the 21 centimeter we are trying to measure. How we measure that? Because the power spectrum is not the observable quantity is the visibility. So if we correlate the two visibility at two different frequency space, that is the delta nu separations, basically the Fourier conjugate of the power spectrum. So we can measure so visibility is the observed quantity, we measure at two different frequencies, and if we correlate two visibility at two different frequency separations, after doing the Fourier transform, we can measure the power spectrum. So that is how it is related with the observable quantity and what we want to measure. So two visibility correlation formalism is the we will use for the power spectrum. So what is the current status of the 21 centimeter observation? This is the summary plot of all the recent upper limit of the 21 centimeter power spectrum. This is the GMRT here in the it is 2013 upper limit, and all the other telescopes MW LOFAR are there. So the most sensitive is now is the Hera one. Yeah, still it is few orders of magnitude in the magnitude higher than the expected signal. What SK will give us? The SK will have the enough sensitivity to measure the signal in the real space, not in the Fourier space that I have discussed in the power spectrum. So this is the simulated, and what SK will look like. We can measure the bubble, the ionized region using the SK, that is have enough sensitivity to measure the actual brightness temperature in the image domain. Now I will talk about our efforts that we have been doing for last several years in terms of the 21 centimeter observations. So again I said the foreground and the noise are the more challenges in the 21 centimeter observations. There is another challenge is basically called the wide field foreground. What is this? We have concentrated a part of the sky, that is the field of view. But even we are concentrated on a small part of the sky, but the residual the foreground, which is quite far away from the center of interest, will oscillate the signal. As I said, the foreground is the smooth component along the frequency, but depending on the instrumental response, basically the frequency dependence of that, it will create some oscillations. So that is the another challenges of the instrument inherent to the instrument. We can't get rid of that. So that is the oscillatory pattern actually in the terms of the because of the instrument response. So somehow we have to remove this smooth the instrumental response to remove the foreground. So that is the wide field foreground we called. So this is the symmetric diagram. This is the primary beam response, and the signal, the foreground is quite far away from our center of location. But what happens because of the primary beam response, this feature will change as a function of because of the primary beam response of the instrument. This will create the oscillations pattern in our frequency dependence. We can't remove the oscillatory pattern using the normal smooth foreground technique. So that's why what we do here, we remove the sky response using some primary beam, some window functions, that is the tapering function with Gaussian functions, to remove the whatever the smooth component, whatever the contribution in the sky outside of the interstellar region, we want to remove them using some window functions. And as the visibility we measure in the Fourier domain, what we do generally convert the measured quantity with the Fourier transform of this window function. So that is the technique we use, basically the tapering, to remove the frequency dependence of the primary beam outside of this region that we are interested. So that is the tapered Gided estimator we have developed to measure the power spectrum. So that is just the mathematical technique. We remove the self correlations also, because the noise is dominated at the self correlations, and it is a highly basically computerly much faster compared to the normal estimator. It's also the side lobes that are basically the outside of the primary beam also remove the noise bias. So we have developed the estimator, and then we have applied this into the data, and that is the upgraded GMRT data we have used for the 20 centimeter measurement. So this is the UGMRT, now the upgrade GMRT. This is the band earlier as compared with the GMRT and UGMRT. This is now quite large bandwidth, and this is the antenna 30 antenna distributions, and this is the 45 diameter each. And as the function, as this telescope rotate, it will fill the whole UV domain. This is the one of the measurement of this galactic synchrotron, which is a large scale emission of using the GMRT, and we use some tapering basically just to observe the large scale mode, and basically this is coming from the fluctuations of the synchrotron emissions, and this is the power spectrum, the angular power spectrum of the synchrotron using the UGMRT observation at the band 2, basically the 150 megahertz, and at some L, up to some L, we can measure the angular power spectrum, and the power law is consistent with the synchrotron measurement, and the high L is basically dominated by the noise. So we can restrict this up to which we can measure the galactic synchrotron. So this is another measurement of the galactic synchrotron using the GMRT. This is slightly off galactic plane at 2 it's a plus minus 10 degree of the galactic latitude, and this is the measurement again using the angular power spectrum, and two region basically this plus minus 10 degree, and we measure the angular power spectrum, and if the slope is consistent uh, with the synchrotron emissions. We have measured the angular power spectrum. Later we have extended our observations to the TGSS survey, all sky GMRT survey at 150 megahertz. So we have used this TGSS survey, the publicly available data, and to measure the angular power spectrum at all over the sky. Basically this is the synchrotron, because the 21 centimeter is still quite it's quite low as compared to the synchrotron. So what we measure, we remove all the bright point sources from the data and measure the angular power spectrum from the left panel is before removing the bright point sources, because this is the mainly isotropic, the radio galaxy is distributed all over the sky. Right hand is basically after removing the extragalactic component. This is mainly the galactic component, the synchrotron, and there is a high intensity at the galactic plane, and these regions are basically the southern hemisphere, which is not able to we can't observe using the GMRT. This is another GMRT observations at 325 megahertz. This is the earlier one is at 150 megahertz. This is 325 megahertz, and we measured this is the image of the sky. This is the Elias N1 field, and we apply the TGE to estimate the angular power spectrum of the synchrotron, and this is the power law as a function of frequency. So there is some power law break at some frequency. Still we are investigating why. But we saw some break in the frequency as a function of frequency. It's not exactly same power law follows the whole range of the angular power spectrum of the synchrotron. So there is some power law break. We are not sure, but we are still investigating the issues. So this is the angular power spectrum. Now, as I said, if we correlate the frequency at two different frequency channels, the angular separations, we can measure the power spectrum after the Fourier transform. So basically, what the problem is that in the GMRT there are a lot. So basically, this is the white region is the flagged at the band 2. These are the only available region in as a function of this is the channel. So only the few persons are available at the band 2 observations for the GMRT because of the RFI and other issues. So if we do the Fourier transform using this type of flagging pattern, we will get this kind of nature, but the signal is here. Because of the flagging pattern, we will not able to measure the power spectrum at this, basically these are the K modes, because of the signal is here. So somehow we have to remove the flagging pattern that is creating this kind of extra features. So what we do generally, we are measuring the Fourier transform, we are correlating the phase, so in this nature, basically we do so the power spectrum you can measure is both ways. Either do the Fourier transform first and then correlate. Later, either you can, or you can measure the frequency separation first and then do the Fourier transform. So this is the delta nu separations. In this way, you can just get rid of the flagging problem, and you can measure the power spectrum. So you see that here, I first measuring the delta nu as a frequency separation measure. Even in the 90% data, 80% data flagged, you can measure the power spectrum quite accurately. So this technique we have used for the 150 megahertz, and we see that this power spectrum in this region is basically consistent with the noise. So again, we use the GMRT band 3 observations and we measure the power spectrum, but there are some issues we are facing, because when we remove the delta, so the next problem will arise because of this correlation of the ALL and RR. This is two different polarization. This signal will also pop up. So what we do is generate the cross correlation, two different polarization observation. If we cross correlate this RR and LL, it will give the more sense of the some correlated part will be get rid of. So that's why we use these cross correlations, and also we remove the some kind of foreground. The Asif will talk about all of this, and this is the final power spectrum from the GMRT band 3. We have removed the foreground using some polynomial fitting, and we have achieved this much power spectrum. So these different lines for the different techniques that I have discussed. So this is basically this is the Stokes I power spectrum, and if we cross correlate this RR and LL, we will get this kind of this power spectrum. But when we remove the foreground, we can go deeper level. So what we are trying, basically trying to improve based on your available data, we are trying to improve our technique, how far we can go toward this level. So we are facing, so we have removed we have removed some of the instrumental effect, then we show another effect. So this way we are just trying to improve our analysis technique so that we can go up beyond it, so that we can go deeper and deeper upper limit. So recently we have started with this MWA also. So this all the results that I have showed for the GMRT band 2 and band 3. So we have started with the MWA data analysis also. This is a 256 element and this is the frequency range. This is the tiles, 4x4 tiles. And we have observed this part of the sky is basically this is the deep scan observations. This is the RA 0 to RA. So this is the total deep scan of the sky. We have observed this RA range 349 to 70 degree with different pointing centers. This is 162 different pointing center, one like this, and then this total region is covered. Total duration is 5 hours per night, 10 nights we have observed, and then this is the flagging pattern of the MWA. Because of the periodic flagging, it will create another this kind of ripple. So this we have removed using some smooth component filtering, and we have, so this periodic flagging is basically creating some horizontal pattern in the MWA power spectrum because of the instrumental response. This is basically the periodic flagging. So Asif will talk about more in the Tuesday, next Tuesday. So this is the power spectrum after removing this smooth component because of this, and then we can see that the power spectrum is much, we can remove. So this is before removing this basically this horizontal pattern, but if we remove this horizontal pattern using this filtering technique, we can go the power spectrum into deeper level. So then we can combine all those pointings one by one. This is for one single pointing. If we remove this, we have add all the component, all the pointings, incoherently average this, then we got all the power spectrum, we have combined all of them, and finally we reached here. So basically this is the first one, and after combining all of these, we can limit, we can go to the deeper level of the power spectrum. So 23 we have 23 pointings center in the sky we have combined, and this is the final upper limit we got from the MW observations. So Souvik is leading this work. So yeah, so the summary is that our main aim is to measure the 21 centimeter power spectrum from the low frequency observations. We have developed the estimator to measure the power spectrum, but there are a lot of other effects comes in because of the instrument primary beam response, flagging pattern, everything. So we are developing the different, we are improving our technique to go to the deeper and deeper level, and we are applying to the real data. So the GMRT band 3, band 2, also we are working on the band 4, and also we have started working with the MWA to finally measure the power spectrum, but still we are quite far away from the signal, but we are working. Yeah, thank you.
For the GMRT part, the UV plane is like not completely covered, right?
Correct, yeah.
So what kind of mode coupling does it lead when you are estimating the power spectrum?
Yeah, so basically one of the problem we face because of this sparse UV distributions, there will be some normalization issue. We are doing the Fourier, basically the convolution in the Fourier plane, and then measure the power spectrum. So that's why, because of the not completely filled, we saw using the validation technique, basically the simulations, we saw some normalization issues in the measured power spectrum. So we have used this improved normalization technique using some unit angular power spectrum. So we use simulations based technique to get rid of this sparse UV coverage.
Okay.
A very nice question. So there is so you showed a plot with a K perpendicular and K parallel.
Yeah.
So why is it the case that K parallel is always larger, the probed K parallel is larger than K perpendicular? So I saw that the K perpendicular runs till K till 1 or something like that.
This one?
Yes, yes. So why? I mean,
Okay.
not this one.
Okay.
I mean, there are other plots too where it showed that K parallel. Yes. So maybe this one too. So the K parallel is always larger than K perpendicular. Why is that?
Okay. So basically, this K perpendicular is depend on the UV, the antenna separations. That is basically the how far the antennas are. That will decide the K perpendicular mode. it is related to the antenna separation between the two antennas. So if your antenna is quite far away, this length will increase. So based on the available antenna configuration of the MWA or the GMRT, this will restrict basically the antenna separation will restrict this range. The K parallel range will be defined by how the frequency resolutions of your observation. So these are coming from the telescope configurations. So the delta nu basically the frequency separation, how much the better resolution in the frequency direction you have, you can increase this range also. So this is totally coming from the telescope configurations. Maximum baseline, that is this one, and the frequency resolutions, that will set this one.
Okay, thanks.